Hey everybody, welcome to our last Friday. I guess it's not Friday, it's Wednesday. It feels like Friday because it's our last lecture ever. Just to remind you, today's lecture is just for fun. So nothing that I say today will be on the final exam unless it's review material. Nothing new that's presented today will be on the final exam. You don't even have to watch this lecture if you don't want. If you're busy prepping for example, the final exam, save it and watch it at the end of the semester if you like. I'm really just doing this because I think you'll find this physics really fascinating, and yet it's tricky, but I think you'll be able to understand it on a pretty deep level as well. Knowing some of the stuff that we've learned over the last 2 semesters, putting it all together. So stay tuned if you'd like to learn a little bit about what's the big deal about Albert Einstein. Why is he considered one of the greatest and most influential physicists of all time? It's because he discovered some of the most astonishing stuff you can imagine that shows the world is much more complicated than we ever thought. That's what we'll talk about today. Real quick before I get into the fun stuff about Einstein, here are the things which are due tomorrow, meaning Thursday, April 30th. The 2 online labs, if you've not already done them, the last sapling homework assignment, and the extra credit for the final exam if you want to do that. Of course, it's extra credit. Make sure you're on top of those things. If you've finished those things, the only thing left for you to do is take the final, and you're done with all of the physics that we've done over the course of the last year. Once again, today's lecture content is not on the final. You do not have to study this. I just think you'll think it's cool. All right, so here's where it all starts. We have to go back to an old idea from Physics 1. That's the idea of a relative velocity. If you measure somebody's velocity, you have to measure it relative to something. Usually we imagine measuring it relative to the ground, right? If a sprinter is running along a track and we say they're going at 12 miles per hour or whatever, not a very great sprinter, but somebody like me trying to sprint along a track, then we're trying to determine how fast they're moving along the track. But you could imagine a more complicated situation if, for example, the ground was moving, right? Imagine getting on a conveyor belt and trying to run. If you're running in the direction of the conveyor belt, you're going to move even faster relative to the ground beneath the conveyor belt. And conversely, if you're running against the direction of the conveyor belt, you might end up just stuck in place. We talked about this in Physics 1 in the context of objects being thrown from a moving vehicle. For example, imagine taking a pitching machine, one of those machines that spits out baseballs, and putting it on the back of a truck. If the truck is driving this way, but the ball is being projected that way, then the ball is going to move very slowly, may not even make it to the guy trying to catch the ball here, right? And that's because, if the ball is projected forwards at 80 miles per hour, but the truck is driving this way at 75 miles per hour, then the truck is taking 75 miles per hour of the velocity and pulling it to the left, and leaving us with only 5 miles per hour of velocity of the baseball moving to the right. On the other hand, if the truck was moving towards the guy and the baseball was going 80 miles per hour, and the truck itself was going 75 miles per hour, I would be frightened to be the fellow with the baseball glove, because now the baseball is approaching me at a total velocity of 155 miles per hour, as opposed to 5 miles per hour. So yikes. You see what I mean? It's simply the statement that when an object is thrown from another moving object, their velocities might combine, or if the objects are going in opposite directions, their velocities might fight one another. This is what we call a relative velocity, and believe it or not, this simple idea is the genesis of Einstein's famous theory of relativity. Let me give you one more example of this that will help understand one of the things that's coming up here. You may also have experienced this phenomenon when you're driving down the highway. If you're driving, here's 2 lanes of traffic. If you're in this lane going 60 miles per hour and someone else is in this lane going 80 miles per hour, they're moving past you, but only slowly. They're passing at 20 miles per hour relative to you. Again, this is what we mean when we say it's a relative velocity. If it helps, imagine what would happen if this other car was also going 60 miles an hour. then they wouldn't be passing you at all. You'd both be going the same speed. You'd be able to look right across from window to window and see them because they would not be moving at all relative to you. So that's the idea of a relative velocity. If you're curious, there's a formula that expresses the notion of relative velocity. It's that the velocity of object A as seen by object B is the difference in these two velocities, being careful to take into account the plus or minus sign. So in this situation, it explains why the velocity of the green car relative to the red car, the velocity of the green car is seen by the red car would be the velocity of the green minus the velocity of the red, which is just 20 miles per hour. Applying this to the top two situations is slightly more difficult because you got to think about the velocity relative to the truck and then the velocity of the truck relative to the ground. You'd have to do it in 2 steps, but you can. All right, so as I say, this simple, relatively simple notion, no pun intended, is the basis for Einstein's theory of relativity. When Einstein was a teenager, and yes, this is actually a picture of Einstein when he was a teenager before his hair got all Einstein-y. When Einstein was a teenager, he used to bike to work, and as he biked to work, he would bike along a train track. And he thought to himself, he was thinking about relative velocity. He thought, when I'm moving with somebody, they look slower, right? So here's me on my bike, and well, here's me on my bike, and here's the train. When the train is going this way and I'm going this way, the train doesn't seem to be moving quite as fast because it has a smaller relative velocity relative to me. If I could bike as fast as the train, I could stay right alongside it. On the other hand, he said, if I'm biking towards somebody, when I come home from work and I'm going the other direction, the train is still going this way, but now I'm biking towards it. Boy, I should have practiced how to draw a bicycle before this happened. And that makes the train look faster, right? The distance between him and the train is closing faster and faster. Okay, anybody could have thought of that. But Einstein's really clever idea that kickstarted all the rest of his thoughts was this. What if we did the same thing with a ray of light? If we could bike at the speed of light, here's little Einstein on a bike. If he could bike forwards at 3 × 10⁸ meters per second, and there was a ray of light traveling through space at the same time alongside him, could he all of a sudden, also moving, of course, at 3 × 10⁸ meters per second, could he look over and see the ray of light like frozen in space, like the same part of the wave that he was riding alongside, the same way that if you drive down the road and you're moving the same speed as the car next to you, you can look over and see the driver in the other car? He wondered, could I look over and see the internal workings of a ray of light if only I could bike alongside the ray of light at the speed of light? It's an incredible question, and the answer has really profound implications for how we understand the universe. So the crazy thing is, we've eventually figured out that that is not what would happen. You cannot bike alongside a ray of light at the speed of light and see the light frozen in space the way that you could just about anything else. That's just not what happens with a ray of light. And this is fascinating. It turns out that no matter who you are or where you are, everyone thinks the speed of light, if it's in a vacuum, is 3 × 10⁸ meters per second. And that's regardless of their own speed, and let me add here, or the speed of the source. In other words, no matter how hard you try, no matter what you do, you cannot put yourself in a situation where you see light traveling through a vacuum at some speed other than 3 × 10⁸ meters per second. To put it another way, if we built the outer space version of that baseball being thrown off of a pickup truck, it might look like this, right? I have a spacecraft traveling this way, and I have a laser which is shining a light towards an astronaut. And the astronaut's got some kind of sensor or mirror or something. Don't worry, he's not going to get killed by the laser. Even though the spacecraft is moving this way, remember with a baseball, the spacecraft moving this way would take some of the speed away from the baseball. It does not happen to the laser. If the astronaut measures the speed of the light reaching him, he thinks it's 3 times 10 to the 8th meters per second, regardless of whatever speed the spacecraft is traveling in this direction. And on the flip side, if the spacecraft is moving towards him, remember that would have made the baseball go faster, but the astronaut will still measure 3 times 10 to the 8th meters per second. That's the only speed that you can measure light traveling if light is traveling through a vacuum, regardless of what else is going on or where the light is coming from or what you're doing. It wouldn't matter if the astronaut himself was moving away from or towards the light. That's the reason Einstein on a bike can't catch up to the light. Everybody measures the speed of light to be 3 times 10 to the 8th meters per second. Now, there are two good reasons why Einstein eventually became convinced that this was true. Here they are. The first, the best reason, physics is an experimental science, so the best reason to believe something is if you performed an experiment that demonstrates it. There's a very famous experiment called the Michelson-Morley experiment that proved exactly this. I unfortunately don't have time to go into the details, but you can look it up if you like. It was very clever. It involved using the fact that the Earth is moving. So a laser light being shined from the Earth in the direction of the Earth's rotation and against the direction of the Earth's rotation should have different properties, but it does not. No matter what you do, you cannot observe a laser traveling at a different speed through a vacuum. Einstein wasn't totally shocked by this because by the time he was old enough to really comprehend this stuff, he also knew about Maxwell's equations, and he knew, as you guys know, right, Maxwell's equations specifically predict one speed of light. It predicts this value. This is how we got 3 times 10 to the 8th, by taking this constant epsilon 0 and this constant mu 0 and combining them like this. Maxwell's equations don't say that's the speed of light unless the light is mounted on the back of a spacecraft. There's no variable in here to represent where the light is coming from. It's just the speed of electromagnetic waves, the speed of light. So from this observation, Einstein built what he's most famous for, which is called Einstein's special theory of relativity. The word special is here. I've got an asterisk just to let you know. It's called special because the first theory of relativity he developed was limited to certain special cases. It applied only to objects moving with a constant velocity. Hey, you remember this. When we first started doing physics, we looked only at objects with a constant velocity too. And then as we got better, we looked at objects without a constant velocity. That's how even great physicists like Einstein learned physics. When he first developed a theory of relativity, he did it for objects with constant velocity, and he later expanded it for objects without a constant velocity. That's called the general theory of relativity. It's much more complicated, though it addresses some of the same topics. And it's just a truly beautiful thing. We'll focus on the special theory of relativity here because it's a good place to start. So Einstein's special theory of relativity is based off of two postulates. He takes two things that he assumes to be true. And then this is where the real genius of Einstein came from, right? It was interesting that he thought about relative velocities. It was very imaginative that he thought about biking along a ray of light. But lots of people have had thoughts like that. Einstein followed through on those thoughts and really rigorously thought about what conclusions he could draw from them. So he said, let me assume two things and see what follows, what must be true as a result. And what must be true is some truly fantastical stuff. Anyway, he assumed the speed of light appears the same to everyone, to all observers, regardless of their speed. So that's the thing that we just saw is experimentally verified. No matter where you look at a ray of light, you will see it traveling at the speed of light if it's traveling in a vacuum. So he assumed that to be true, and that seems fair. The only other thing he assumed is that the laws of physics are the same for all observers, that the laws of physics are not suddenly different just because you happen to say, get on a bicycle. I think this is also quite uncontroversial, right? It would be nearly unimaginable if this wasn't true, because how could we even discuss what the laws of physics were? It wouldn't even make sense to do physics if the laws of physics weren't the laws of physics. So with only these two things assumed to be true, Einstein discovered some truly bizarre things about the universe. And I want you to remember these as we go forwards, because some of the stuff that I show you that he discovered is going to look really weird to you. And it's going to seem totally implausible, and you're not going to want to believe that it's how the universe works. You're going to think, really though, isn't this just a theory? And I want you to remember, it's a theory that's based exclusively on these two postulates. So either the theory is true, or one of these things is false. We're already almost positive that this is true because we can prove it with experiments. And it's unimaginable that the second thing would be false. So as long as you believe those two things, the rest of the stuff we see here is also a true property of our universe. Okay, so with what remains of the lecture here, we're going to look at the 5 weird predictions Einstein was able to make based on those two postulates. And again, some of these are going to get pretty weird, but you either have to believe them or you have to disagree with one of those two postulates. Let's explore them. So the first one you've already met, and that's that mass and energy are two measures of the same thing. Unfortunately, it's going to be a bit too complicated for me to show you how this is the famous E equals mc squared equation. It's going to be a little bit too complicated in the scope of this lecture for me to show you why this is true as a consequence of those two postulates, but it does follow from them. I'll be able to just hint at it ever so slightly at the end of the lecture, and you can ask me more about this outside of class if you're interested. But I wanted to start with this one because it's probably the most famous, and because you might want to know that this is where this comes from. Einstein's signature equation was part of this theory of special relativity that he developed based on thinking about the speed of light. All right, now for the good stuff. The second weird prediction that Einstein made is that being simultaneous is a totally subjective thing. In the sense, subjective in the sense that it depends on your perspective. It depends on the eye of the beholder. This is hard to believe, right? I remember when I first learned this. I think in some ways this is the most radical of Einstein's predictions, because it just feels like there should be an unambiguous answer to the question, did these two things happen at the same time or not? And the answer is there's no way to know without specifying whose perspective. If you say, did these two things happen at the same time, you have to say, did they happen at the same time from my perspective, or from the perspective of someone in a spaceship, or from the perspective of someone on a train? Otherwise, the answer might be different. And as crazy as this sounds, I think with a really crappy cartoon, like this one here, I can show you why it must be true as a consequence of those postulates. So imagine a guy on a train. Here he is. And this is a weird train. He's doing a weird experiment. On this train, he's got 2 guns that are going to fire bullets in opposite directions. Right? So the bullets are going to travel through the air, and they're going to hit the sides of the train. Just to be on the safe side, let's put our little guy under some sort of table or protective bunker or something. He's not going to get shot. Now, in addition to these bullets, the guns shooting the bullets, I've got lasers mounted in both directions. Just to be clear, these are lasers, these are guns. The lasers are going to shoot laser beams out in both directions. By the way, this is absolutely nothing what a real laser looks like, but it looks cool, right? Like, it looks kind of sci-fi. The lasers are going to shoot lasers out in both directions. Now, if you are this guy on the train, the guy on the train thinks the following 2 things. First, he thinks both bullets hit the walls at the same time. Right, because I forgot to say, but this thing is exactly in the center of the train. So this is the same distance on each side. The bullets are fired at the same speed. So certainly the bullets hit the walls at the same time, right? Now, this guy also thinks both lasers hit at the same time. for the exact same reason, right? The lasers certainly have the same speed, that speed being 3 times 10 to the 8th meters per second, and they're traveling the same distance, so of course they get there at the same time. So far, so good. But now let's talk about things from the perspective of this guy. This guy is outside the train, looking in. Imagine the train's got a big glass wall, so he can see everything that's going on in there, right? Now, this guy thinks two things. He thinks both bullets hit at the same time. The same thing that the guy inside the train thinks. So far, so good. Let's just make sure we understand, though, why he thinks that. Because here's the thing, it's a train, so the velocity of the train could be moving. Let's imagine the train is moving to the right, so it's traveling past. This guy is just watching it go past him, standing on the side of the train tracks. If the train is moving to the right, then the guy on the outside thinks this bullet is moving faster because it's going with the train, right? V bullet 1. And he thinks this bullet is moving slower, V bullet 2, because it's moving against the train, right? This is the same as the baseball is being thrown from the back of the pickup truck. If you go with the pickup truck, it enhances your velocity. If you go against the pickup truck, it decreases your velocity. So he actually thinks this bullet is faster. On the other hand, he also knows that the train is moving forwards. So the front of the train has moved forwards, and this first bullet has to travel further. So he thinks it's faster, but it travels further, and those two effects end up canceling out. It's traveling just fast enough to make up the extra distance in the same amount of time. Likewise, this bullet is slower, but the train moves forwards during this time. This is the new back of the train, so the bullet doesn't actually have to travel as far from his perspective before it hits the back of the train. He still thinks they hit at the same time. Now, what does he think about the lasers? He thinks the lasers do not hit at the same time. Why? Why would that be? Because remember, everybody thinks a laser is moving at 3 times 10 to the 8th meters per second, no matter what. So this laser here, the one that's going in the direction of the train, is not faster. Remember, light is weird like this. It does not get the benefit of the boost from the pickup truck. It is moving at 3 times 10 to the 8th meters per second, despite the fact that it's on a moving train. Also, this laser is moving 3 times 10 to the 8th meters per second. It is not slower. Everybody agrees on the speed of a laser. That was one of our 2 postulates. That means this laser travels a short distance. This laser travels a long distance. So this laser hits first from the perspective of this guy. This laser hits later. So boom, we've destroyed the idea of simultaneity. The guy inside the train is absolutely positive that the lasers hit both walls at the same time. The guy outside the train is absolutely positive that they don't hit at the same time. So whether things happen at the same time or not depends on whether you are sitting still or on a moving train. It depends on the frame of reference you're viewing it from. Now, I should add here to be clear, sometimes people think this is weird. Sometimes people think I'm saying light is really special in this regard. I'll try to clarify this a little bit more later. It turns out, actually, the bullets don't appear to hit at the same time from this guy's perspective either. It's one of those things like quantum mechanics. You don't notice this effect on an object unless the object is moving close to the speed of light. So it's very easy to notice it for light because light moves at the speed of light. For things that move much, much slower than the speed of light, and yes, even bullets are much, much slower than the speed of light, it'd be very, very hard to tell. The effect is much smaller, but it is there. Nothing is actually simultaneous, irrespective of your frame of reference. All right, are you hanging in there? Are you okay with the fact that the word simultaneous actually doesn't have a well-defined meaning for everybody? That you can say things are simultaneous from your perspective, but just because you say that doesn't mean they were simultaneous from my perspective. It's okay if you're having trouble absorbing that. I think I was halfway through grad school before I fully got my brain around it. But hey, we're going to keep going with yet another weird prediction that Einstein came up with. Einstein took the idea of once Einstein realized the idea of simultaneity was faulty, or at least was context dependent, then he realized that this means time itself must be subjective, in the sense that it depends on who is experiencing it, on the point of view of whoever is, that it can differ from different people's points of view, right? Because simultaneity is a property of time, and if simultaneity is gone, there must be something wrong with time. Not wrong, just different than what we expected. So his third weird prediction was that time passes more slowly if you're moving really fast. In other words, if you want to live forever, just run as fast as you can, because your personal clock will be moving slower while you're moving quickly than it would for somebody sitting still. Physicists like to joke that this is the real reason why exercise is good for you. Of course, I'm joking. Let me see if I can show you. I think I can show you pretty convincingly why this must be the case in terms of some basic physics based on the things that we now know to be true. So imagine another bus or train or something like that, which is moving. Let's make it a bus this time. It's got some velocity going to the right. And we're going to build a weird kind of clock. What we're going to do is we're going to put two mirrors, one on the ceiling and one on the floor. And we're going to bounce a laser back and forth, up and down between these two mirrors. That's easy enough to do. You shoot the laser beam and then you replace the laser with a mirror, and then it just bounces back and forth between the two of them forever. How is this a clock, you might wonder? Well, maybe, let's say this, it ticks each time light hits the bottom mirror. Sorry, handwriting getting really bad. Right? This thing is doing the ticking. So light goes up and down, tick, up and down, tick, 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 tick. That's a clock, right? I can make each of those ticks last a second or 100th of a second or whatever time period I want. And that's going to be based on the size of the clock, right? We figure out how long it takes the light to go up and then back down, and then we know exactly how long a tick is going to last. And that ticking is my clock. I could use that to measure time. But what if you're somebody standing outside the bus, looking in at this clock? From your perspective, as the laser leaves the ground, it goes up, but it's also moving to the right, right? It's got two components to its velocity. I told you we were going to go back and revisit some Physics 1 stuff. It's moving upwards. We know it doesn't just move upwards and back down, because if it just moved back down, by then the mirror would have moved over and it would miss the mirror. So obviously, if we see the light actually hit the mirror again, just to be clear, here's the original bus, and then here's the bus a few moments later. So the mirror starts over here and then it moves over here as a result of the motion of the bus. This is all from the perspective of someone inside the bus up top. This is from somebody outside the bus. From outside the bus, you see the light go up and to the right, because the bus is going to the right. Think of this also, we had a clicker problem last semester about jumping in a moving bus. You still move forward with the bus, and then the light goes back down and it hits the mirror. This is the mirror's new location. It's not two different mirrors. The mirror moves forward. Let's label it like this, mirror. The mirror has moved forward, the light goes up, hits the mirror up top, comes down, hits the mirror at the bottom, and of course this causes a tick. But how frequently does this thing tick? Well, from this person's perspective, the light has to travel further. Do you see it? Because it has to go along this diagonal path, which is longer than just this vertical path. So how long does one tick last? Well, if you're inside the train, you think this is how you calculate one tick. You think you take the height here, and you calculate velocity equals distance divided by time. The velocity here is the speed of light, so the time is the distance divided by the velocity. If you're outside the bus looking in, you also think the time is the distance divided by the velocity, but you think the distance is this larger distance, d. So you think it's d over c. And remember, you both have to agree on c. So if you agree on c and you disagree on the distance, you must disagree on the amount of time. So literally, this fellow's clock is ticking at a different rate than this fellow's clock appears to be, even though they're both looking at the same clock. Now, sometimes people see this and they think that what I'm describing is a weird clock that wouldn't work very well because it would depend on whether or not it was in a moving bus. But if you think a little bit more deeply about this, and I really encourage you to think about this, right? Suppose the guy on the bus has a different clock. He's got his own, he uses the stopwatch on his Apple watch or his Apple iPhone or something, right? Apple didn't pay me to say this. He uses an Android phone too. He turns on his stopwatch and he should be able to synchronize it with the clicking of his laser, right? He should be able to see, okay, every time the laser clicks, that corresponds to a millisecond on my stopwatch. Well, if this guy tried to do the same thing, he would find that his stopwatch was getting out of sync with the laser, even though the exact same Apple Watch owned by the guy on the bus is not getting out of sync with the laser. So it's not just the laser. Even if we compare things based on another device, we wouldn't agree. And now, let's take it a step further. Suppose these guys put their fingers on their necks and they feel their pulse. And they look at how many times their heart beats each time the laser goes up and down. The guy inside the bus is going to get a different answer than the guy outside the bus. In other words, even if they both just finished doing the same exercise and had the same heartbeat before one of them got on the bus, now they aren't going to agree as to whose pulse is beating faster. And this means, if you think about it, time is literally running slower for the guy on the bus. He literally is going to count his pulse rate differently. The guy outside the bus is going to think it takes longer for the guy inside the bus to have a heartbeat. It looks like his heart rate has slowed down. And that's true for all the metabolic processes in his body. It's true for everything. Anything you can time looks like it's moving slower from the perspective of the guy outside the bus. This little bit of weirdness here, this idea that time might move faster or slower for some people, is called time dilation. And here's the mathematics of it if you're curious. Again, you do not need to know this for my exam or the MCAT. It's just for fun, but some people might be interested. There's an equation that compares what we call the proper time. The proper time is measured by someone, the fancy term is in the moving reference frame. This means on the bus. Somebody on the bus measures a certain amount of time, right? They turn on their stopwatch and they try to measure 10 seconds. And then if you compare that person to the amount of time measured by somebody else during the exact same time increment, they will get different answers. The way you calculate the different answer is using this complicated equation here. This number here, it's a Greek letter gamma. This is called the gamma factor. Sometimes also called the Lorentz factor. It's a measure of just how much time gets distorted. What you do is you take 1 and you divide it by the square root of 1 minus v squared over c squared. V is the velocity of the bus. C is 3 times 10 to the 8th. Oops, 3 times 10 to the 8th. So you can see if v is a very small number, if the bus is only moving, 1 meter per second, then this is a very small number, 1 divided by 3 times 10 to the 8th, and then I square it, it's tiny. So if this is tiny, then 1 minus this is basically 1, and the square root of 1 is basically 1, so that's 1 divided by 1. The gamma factor is almost exactly 1 if your velocity is small. And this is why nobody noticed the gamma factor for a really long time. You got to be moving at a velocity near the speed of light to really notice the gamma factor. But if v is not small, gamma becomes a really big number. And here's the equation for time dilation. The time that passes off the bus equals the time that passes on the bus times gamma. So they're not the same time. And the bigger the gamma is, the bigger the difference between the two. And again, I have to point out, this is not a funny quirk of the way we designed the clock. What I'm saying is that if the person on the bus figures out how much time is passing based on their clock, maybe not even based on their clock, right? They just calculate correctly how long it should take the light to go up and down. And using that time period, they use that to time how much time passes between one heartbeat and the next. The person outside the bus could make the same calculation and draw the same conclusion about that person's heart rate, and they would think that it had taken much more time for their heart to beat. In other words, they would have thought that a really long time, if the bus is moving really fast, at least, they would have thought that a really long time was passing between the heartbeats of the person on the bus, despite the fact that they were still alive. Now, as I say, the speed of a bus is quite small, so you're really not going to notice this effect on a bus. But let's look at what could happen in some more extreme situations. Suppose a spacecraft were to travel from the Earth to some distant star, and it travels at a velocity which is 99.9% of the speed of light, 0.999 c, away from the Earth. If the folks on the Earth look at that rocket ship and think that it takes the rocket ship 50 years to get there, and unfortunately, those are the kinds of timescales it takes to get to any kind of nearby star, even if you're going extremely fast. If you look at that and you think it took 50 years on the rocket ship, how long does the crew of the rocket ship think that it took? I'm asking you the time measured by the crew of the rocket ship, so that's T0, what we call the proper time, the time measured by people on the moving vehicle. So to figure this out, we're going to need that gamma factor. Gamma is equal to 1 over the square root of 1 minus v squared over c squared. And v in this case is 0.999 c, 99.9% the speed of light. So I'm going to take that all and square it. The c's will cancel, and I just get 1 over the square root of 1 minus 0.999 squared. Do this calculation yourself. I think you'll find that the gamma factor is 22.37 approximately. 22.37. That's how much time, how many times slower time is running for the people on the spaceship. So since time outside equals gamma times the proper time, and the people on Earth think it took 50 years. I don't know why I suddenly used cursive here, 50 years. 50 years equals gamma, 22.37, times the proper time. The proper time is only 2.24 years. That's a huge difference. The people on the spacecraft think they were only on the spaceship for 2.25 years, less time than most of you have been in college, and they arrived at a total different star system. Meanwhile, an entire generation has passed back on Earth. So if you get up really close to the speed of light, like 99.9% the speed of light, you can get an enormous difference in the experience of time between people on a moving vehicle and people not on a moving vehicle. Interestingly, if we ever are able to explore deep space, like other planets outside our solar system, we'll probably have to make use of this kind of trick. Right? Because even though you and I might see a spacecraft leave Earth and never arrive at its destination in our lifetimes, if it only takes a couple of years from the perspective of people on the spacecraft, then at least some human beings can get there in their lifetimes. It's kind of a crazy but totally plausible way of reaching distant stars. Now, I should warn you, traveling at 99.9% of the speed of light is extremely difficult. I have no idea. It would be very, very hard to get a spacecraft moving that fast in the first place. But the faster we get the spacecraft moving, the more we can take advantage of this time dilation. And even if the people back home on Earth can't see the spacecraft arrive, at least the people on the spacecraft will get there before they're old. Now, you want to know something slightly funny? This is Mark and Scott Kelly. I think this is Scott, and this is Mark. They are both astronauts. Here they are after Scott has gotten back from nearly a year in space aboard the International Space Station. I think it was 342 days. While he was on the International Space Station, he was traveling about 7,500 meters per second faster than Mark, who was just back on Earth. And because he was moving faster, if you do the calculation, you'll discover that during this time, Scott became about 8.6 milliseconds younger than his twin brother, Mark. That number actually includes a little bit of an additional effect from the general theory of relativity, but you get the point. So despite having been born as twins, their actual ages in terms of how many cycles their cells have gone through and all that jazz are now different. It's only different by a few milliseconds, sure. So we're not going to notice the difference. It's not like that's the reason Mark has a mustache and Scott does not. But it's an interesting little demonstration, and it gives people an idea of how you could notice the difference. So this is about the time people start just not believing this, because this all sounds like science fiction. I assure you, to the best of our knowledge, this is all true as a description of how the universe works. And I would like to point out, in my opinion, Einstein's theory of relativity is perhaps the most extensively tested theory in the history of physics, maybe in the history of science in general, and it's always stood up to the tests, except for the places that are now filled in by his general theory of relativity. We have very, very good reason to believe it's true. Here's one of the best known ones, though it's no longer considered the absolute best evidence, but it's a great thing to point out. A pair of scientists named Heffley and Keating, in 1971, they performed a version of sending one twin astronaut into space. What they did was they took two twin atomic clocks, two ultra-precise atomic clocks that were accurate down to the nanosecond. They synchronized them. They put one of them on a super fast jet, and they let it fly around the Earth for 45 hours. So one of the clocks was moving really fast, and the other one was just sitting at home. When they brought the plane back down for a landing and took the clock off the plane and compared them, they discovered that the clock on the plane had a different time than the clock on the ground by several hundred nanoseconds, which is not very much time, but these clocks are ultra-precise clocks that never lose more than a nanosecond. So losing several hundred nanoseconds was quite surprising. And there was much more to the experiment than this. They worked very carefully. They looked at what happened when the clock was flown with the rotation of the Earth versus against the rotation of the Earth, because the clock on the ground is also moving because of the rotation of the Earth. They took the general theory of relativity into account, and everything that they found to within, at least within about 10% precision, agreed with exactly what Einstein's theories predicted. And we've since performed other versions of this experiment to much higher degrees of precision as well. All right, we're almost done. We're past the halfway point. We have two more weird things to go. The fourth one is this: things that move past you quickly are shorter. Notice I don't say look shorter, I say are shorter. Here's one way to think about this. Think about that spacecraft traveling to the nearest star system. Here's the Earth, and here's a distant star, and here's that spacecraft heading there. We think this took 50 years. The spacecraft thinks this took 2.24 years. But we both agree that the speed was 0.999 c. So if we all know how fast the spacecraft is going, how could they possibly have covered the same distance in different amounts of time? They just could not have. The only possibility is that the physical distance passing them, this distance, is shorter, not looks shorter, for the people on the spacecraft. They don't agree with us about how far they actually had to travel to reach the nearest star. They think, surprisingly, once the spacecraft started moving really fast, space scrunched up around them, and next thing they knew they were there in only a couple years, even though when they were on the ground, they also thought it would take 50 years for them to get there. Stuff that moves past really does look shorter. This is the little cartoon that I used to help me remember this. Here's me on the ground watching Superman. As Superman moves past me, from my perspective, he really is shorter. He really is scrunched up like this because he's moving past me really fast. On the flip side, from Superman's perspective, notice this is actually Pi Man, no copyright infringement intended. From his perspective, all the trees are shorter, right? I think this tree is really wide and Superman is scrunched down to be nearly the width of the tree. He thinks the trees have been scrunched down to be much, much narrower than himself. We're both correct from our own perspectives. So this effect is what's called length contraction. It's like the length version of time dilation, and except instead of making the time last longer, it makes distances look shorter. But the calculation works very similarly. You compare not the proper time, but the proper length. This is the length measured by someone who thinks they're stationary. Basically, it's the length of the person themselves. This is the length of Superman. You compare the length that Superman thinks he is, L0, to the length that someone else would measure watching him go past. You calculate a gamma factor in exactly the same way, and the length seen by me on the ground equals the length that Superman thinks he is. I should have said not the length of Superman, the length Superman measures for himself. Right? While he's flying through the air, he whips out a measuring tape and measures from his toes to the top of his head. And he gets, 6'10", or I don't know how tall Superman is. Plug that length in here. Divide by gamma, which makes it much smaller, and that's the length that I will see as he flies past me. You might wonder, how is that possible? Surely I could look at the measuring tape that he's carrying and see his actual length. No, if he's carrying the measuring tape, it's also moving however fast he's moving. So it's also been scrunched down. So what used to look like 1 foot has been scrunched down to a shorter distance. I think when he tells me he thinks he's 6'10", from my perspective, it looks like it's because he's using a really defective measuring tape where each foot is only a couple inches long. And last but not least, I promised you 5 weird predictions. The 5th is actually one we already knew, but now we can understand it just a little bit better. The 5th prediction is nothing, no object anyway, can move faster than the speed of light in a vacuum. I don't care what you do, you will never be able to move yourself or a rock or a proton faster than 3 × 10⁸ meters per second. Here's why. Einstein's equation E = mc squared it's actually a little bit more complicated than that. It actually, you might think of it as saying E0 = m0 c squared. So E0 is the energy you have when you're not moving, energy you have at rest. M0 is the mass you have when you're not moving. You're going to protest, surely my mass doesn't change just because I start moving, at least not till I start burning calories. And I have to disagree. According to Einstein's theory of relativity, your total mass depends on how much you're moving, at least depending on how you measure mass. Your so-called rest mass, we can all agree on what your mass would be if you were sitting still, and that's usually what we refer to as an object's mass. But Einstein's real equation says total energy, that's rest energy plus kinetic energy, your total energy, equals that gamma factor times your rest mass times c squared. So we could rearrange this and write, let's see, let's not do that. Let's just put it this way. The energy that you have to have this particular mass and move at a particular velocity depends on this gamma. And notice what happens if I try to move at the speed of light, so v = c. Then gamma equals 1 over the square root of 1 minus c squared over c squared, which is 1 over the square root of 1 minus 1, which is 1 over the square root of 0, which is division by 0. At the very least, this is not allowed. And basically, it's going off to infinity. The closer v gets to c, the closer gamma gets to infinity. If gamma becomes infinity, then the energy you have also becomes infinity. In other words, it takes an infinite amount of energy to move at the speed of light. That's why nobody can do it. If you try to move at the speed of light, it will take more and more and more energy, and not just the old-fashioned 1/2 mv² kinetic energy. That's the kinetic energy that you have if you're ignoring the effects of Einstein's theory of relativity, which is safe for small velocities, but not safe for large velocities. The real kinetic energy you have with a large velocity is related to this equation here, and it becomes infinite. There's one exception, of course. Even if gamma is becoming infinite, you might escape this paradox if you are massless, like a photon. Hence, massless things like photons are the only things in the universe that can move at the speed of light. All right, my friends, that is it. You have reached the end of Physics 2020, the end of your introductory physics sequence, the end for many of you of our 2 semesters together. I hope you've enjoyed it. I'm sure there have been some ups and downs. I know that we've asked a lot of you and that we've really pushed your brains. We've required a lot of work. You've put in a lot of hours. And all I ask is that in addition to thinking about how difficult and how challenging it's been, you take a moment to think about how much you learned along the way. and that you see at least a few of the things that we learned as, if not even useful, then just interesting. I hope that you're the kind of people, you become the kind of people, if you weren't at the outset, who can see why it's cool to want to dig into these questions of how does the universe work? What's truly going on in a ray of light? Is time really flowing the way we think it is, or is time a matter of perspective? These are beautiful, profound questions. People like me who get to think about them for a living consider ourselves very lucky. And I hope you see now that all the time you put in answering questions that maybe didn't feel so beautiful or profound, like just calculating velocity equals distance over time. Well, you had to learn how to do that to be able to understand the lecture about Einstein's theory of relativity today. All of this stuff was revolutionary in its time, and it will be necessary to understand the next revolutions in how we understand the universe. You are all now people who are equipped to understand whatever those next steps may be when physics continues to evolve, when science continues to evolve. And I hope also you are the kinds of people who will be helping to make those steps forward. Maybe not in physics, maybe in medicine, maybe in biology, maybe in some totally different field. But if you've gotten through this course, you've certainly demonstrated, regardless of the grade you got, you've demonstrated you're the kind of person who can hang in there. If you can complete and pass the course, you are the kind of person who can do this kind of stuff. And the world needs people like you doing this kind of stuff in physics, in medicine, and biology now more than ever. Hey, it was a privilege to be a professor for you guys. Thank you all for all the time we spent together, all the wonderful pictures you've sent me in the last few months to keep my spirits up during the quarantine. This semester has been one unlike any other and will always be in my memory. You guys have a special place in the history of physics at the University of Colorado, and in the history of physics as I remember teaching it as well. Thank you all for everything. Good luck on the final exam. I'm proud of each and every one of you, and I can't wait to see what you do in the future.